All right, welcome AP students to your gas law AP problem walkthrough video. So you guys have just learned about calculating gas pressure, Dalton's partial pressure law, and the ideal gas law, as well as deviations from ideal gas behavior. So we're going to go over that with a few conceptual questions and then one full short FRQ question, AP style. Again, this one might actually be valuable for you to watch the conceptual questions beforehand because the AP question doesn't address everything, at least from the one that I selected. Or of course, you can just, do it on your own for that curve. So either way, though, there's also going to be AP classroom quizzes released on AP Classroom if you want to have even more practice, considering that this is one of the biggest units that the AP pulls from. So let's go at page 4, question 15 in your workbook. Here we have synthetic diamonds can be manufactured at a pressure of 6.00 times 10 to the 4th ATM. If we took 2 liters of gas at 1.00 ATM and compress it to a pressure of 6.00 times 10 to the 4th ATM, what would be the volume of that gas? So first thing you should notice is that we're really dealing with 2 specific variables. We're relating volume and pressure. And because it hasn't told us otherwise, we can assume that all other variables are constant or fixed. So when looking at the ideal gas law, what we know is that PV equals nRT, right? Or what we could do is we could simply write it PV over nRT, right? And if we're talking about a change, a dynamic state, it would be kind of like saying P1 V1 equals nRT divided by nRT equals P2 V2 all over nRT. And because these are fixed, the nRTs, the mole amount, the R constant is of course fixed, and the temperature, what it would become like is that you would get that this denominator ends up canceling out because it becomes like a constant 1, and you would get this isolated, okay, equation that P1 times V1 equals P2 times V2. And we call this, I believe, Boyle's law. Oh man, now I'm like questioning myself. Let me double check really quickly. Okay, I was right. It's Boyle's law. I shouldn't have doubted myself. So we call this Boyle's law. And this is the isolated relationship between pressure and volume when we see a dynamic change, okay? Or a shift from initial to final condition. So what we then do is we just simply plug and chug. These are some of my favorite problems when you just plug in the variables that you know and you solve for the unknown. So I'm going to manipulate my equation first just to isolate the variable before I start actually inserting all the numbers. So V2, I'm looking for my final volume. So V2 is going to equal V1 times P1, initial conditions, all over P2. And I get that if when putting in the numbers, it's 2 liters times 1.00 ATM, just for sig fig tracking, divided by 6.00 times 10 to the 4th ATM. And we get left with V2 is equal to 3.33 times 10 to the negative 5th liters. All right. So pretty simple. It's just a manipulation of the ideal gas law. And instead of having a static state, we turn it into a dynamic initial versus final state. And we isolate the variables that are changing. And we assume all other variables are held constant or fixed unless told otherwise. So how about number 19? So this is a question, all right, where we see when do you release when you do release the predicted amount of moles to theoretically bring the air at -5 degrees Celsius and 1.5 atm, the temperature and pressure are slightly different than what were expected. Why would that happen? So immediately you want to identify that this question is an deviation from ideal gas law question. From ideal gas, I should really say behavior question. Okay, based on these key terms, it was a theoretical prediction. And then what we see is that we're slightly different. All right. And it's talking about properties regarding a gas, temperature and pressure. So what we see is that the temperature and pressure are slightly different. Why would that be? We're not really told exactly how they're different, but we are told that we have the air temperature to be a really low degree Celsius, -5 degrees Celsius, and a pretty low pressure. Well, that's actually close to standard pressure. That's higher than standard pressure, actually. Just kidding. That's higher than standard pressure. Standard pressure is 1.0 atm, and we're at 1.5 atm. So what we're seeing is conditions that are less favorable for allowing a gas to act like an ideal gas. So we would say then the deviation from predicted, okay, behavior, or another way of putting it is ideal gas, right? From predicted behavior or ideal gas law, okay, expectations, would be due to the lower temperatures creating an environment where particle collisions are less frequent, which would impact the pressure, and more IMFs could be experienced, right? Because if you're slowing down when you do collide, you might have an potential for increasing the stickiness. Okay, so all right, so moving on to question 20. How do you calculate the partial pressure of one gas in a chemical reaction when you know the partial pressure change of another gas, right? Any relevant equations. So here, this is kind of more truly just purely conceptual question where I want you to understand and where the AP wants you to understand. What are the necessary equation when you're asked to look at the particular contribution of one gas in a mixture of gases? Okay, and that's where Dalton's law of partial pressure comes into place. And the equation goes that the total pressure of a mixture of gases is equal to the individual pressures of each gas. So the pressure of a hydrogen 2 gas plus a pressure of the nitrogen 2 gas plus the pressure of the NO2 nitrogen dioxide gas together create the sum pressure that's going to be measured, all right, according to some barometer or so forth, right? We could also figure out, let's say we don't have the individual pressures of each gas to just solve for the unknown variable of one, but we do know the mole ratio, or what we call is the mole fraction of a gas. We do know, okay, well, I might not have measured out the individual pressures of each gas, but I do know, okay, that in this sample, I have this amount of moles of this gas, and I know that my total sample has this amount of moles of gas in general. And so what we can do is using the concept of mole fraction, if we don't have the individual partial pressures, we can say, well, whatever pressure contribution my single gas A is providing is going to be equivalent to the fraction, the mole fraction of that gas, the mole percentage of that gas present in mixture times the overall pressure measured. Okay, so what we could do is we could use a combination of these three kind of derivations and equations to identify the relative pressure contribution of an individual gas in a mixture. So that's kind of your conceptual overview. Let's go ahead and head to AP problems. And we're going to head to question number 5. It's a short FRQ. It should take only about 9 minutes and it's worth 4 points on the AP. So what we have here is a student is doing an experiment with CO2 gas. Okay. Originally, a sample of the gas was in the rigid container at 299 Kelvin and 0.70 ATM. The student increases the temperature of the CO2 in the container to 425. So describe the effect of raising the temperature on the motion of the CO2 molecules. So we know that from the kinetic molecular theory, if we're assuming ideal behavior, all right, so assuming ideal gas behavior, and according to kinetic molecular theory, you would probably want to write that out in your FRQ, but I'm just going to save some time. The temperature is directly proportional to the kinetic energy of a gas sample. So the molecules would have greater kinetic energy, all right, and speed up. And another way to put it is greater average speed or velocity, right? Greater average speed at higher temperatures. All right. 2, calculate the pressure of CO2 in the container at 425 Kelvin. So what's interesting about this is we don't know very much information, but we do know temperature and pressure. That's what we're given. And we know it's a dynamic change. So what we're looking at here is Charles' law, the isolation where we assume all else being equal, number of moles of gas particles and volume. And it says we're in a rigid container, so that is confirmed. And we're talking about the same sample of gas. So that is also confirmed that N for moles of gas and volume is indeed constant in this problem. So then what we do is, since we have a dynamic initial versus final, we set up our relationship. We know that according to the ideal gas law, P and T are directly connected. And if we're talking about the change from initial to final, what we see is that P1 over T1 is going to equal P2 over P2. So then what we do is we just simply plug in and I'm probably actually going to rearrange to solve for P2 first. So P2 is equal to P1 times T2 all over T1, which is going to equal 0.70 ATM times 425 Kelvin all over 299 Kelvin. And remember, with ideal gas law problems, we always want temperature should always be in Kelvin for any ideal gas law calculations. And we get the value of P2, and I already wrote that, is equal to 0.99 ATM. And that would be your answer to the correct sig figs. All right, next one. In terms of kinetic molecular theory, briefly explain why the pressure of the carbon dioxide gas in the container changes as it is heated to 425 Kelvin. So what we know is that, okay, according to KMT, all right, temperature, a raise in temperature, all right, a rise in temperature, okay, whoops, temperature creates or results in, I think it's a better way of putting it, results in increased kinetic energy and motion of particles. Okay, the increase in motion leads to increase in collision. Okay, increase in collision, i.e. more frequent collisions and more forceful collisions because there's more energy behind each interactions and more forceful collisions, resulting in increasing pressure or resulting in an increase in pressure. All right. D, the student measures the actual pressure of the carbon dioxide in the container at 425 Kelvin and observes that it's less than the pressure predicted under ideal gas law. Explain this observation. So this is another deviation. And here we have pressure being less than expected, right? So what we know is that there are a couple main things that we attribute for deviations. Deviations are often attributed to one, IMFs, okay? And two, volume of gas particles. That's kind of like usually the main reasons that we tie back to when we try to explain deviations. So what we see here is for us, the pressure of the gas sample is less than ideal gas expectations or predictions due to, all right, the attractive forces experienced between the molecules, creating or resulting in inelastic collisions and less pressure produced. Okay, so again, this was another FRQ that was really heavy on explanation base. When you write an FRQ, don't forget to state the laws that you're doing. Don't leave it up to assumption. Just tell them. If you're talking about the kinetic molecular theory, tell them that. If you're talking about this relationship, tell them that. Don't do a roundabout answer. Just tell them exactly what principle you're building off of and how it directly applies to answering your question. So good work, you guys, and best of luck.